Okay, perfect. Okay, well, welcome everybody to another MCRN Colloquium. Today, we're lucky to have Dr. Gonzalo Gonzalez de Diego speaking to us today. He got his PhD in 2020 from the Mathematical Institute at the University of Oxford under the supervision of Ian Hewitt and Patrick Farrell. His thesis focused on viscous contact problems with applications in glaciology. But today, as a postdoc at the Courant Institute at the University of New York, he'll be talking about sea ice this time, and in particular, computational interface of a continuum model for sea ice from data. So with that, please take it away.
Thank you, Christian, and hi, everybody. Thank you for joining. Before I start, I would just like to say that since we have 45 minutes and my presentation might not even make it to 45 minutes, please feel free to interrupt at any moment. I really prefer that. And I also just see my presentation, so I won't be able to see it if anybody has a questions or if anybody's sending a message. So yeah, just feel free to interrupt at any moment. And with that, I'll start. So I'll be talking about work I've been doing in the last year with my postdoc supervisor, Georg Stadler. And it's all about inferring continuum models for sea ice from data. And yeah, just here I just have a little information about us. I'm a postdoc at the Courant Institute. Georg is a professor here at the Courant Institute. And we're both part of the Sea Ice NURI project, which is funded by the Office of Naval Research. And I would like to give thanks to Reza Malik Madani, who's our contact there at ONR, who we have great conversations with and who suggested I speak at this colloquium. If anyone wants to see anything else, or wants to read more about this project, feel free to go to the website. It's a bunch of us working there, and I'll mention some of our collaborators throughout this talk because I think the work is quite interconnected, but I think we've managed to establish quite rich collaborations, which has been very exciting. This is the outline of the presentation, very simple. I'll be giving an introduction that will be relatively long. I'll just talk about sea ice modeling to kind of set the ground for the work I'll be talking about. The theoretical aspect of this work will be part 2 of the presentation, this rheology inference framework, where it gets a little bit more mathematical, but I've really made an effort to keep it as simple as possible. And then I'll show you a bunch of numerical results where I'll just try to convince you that our framework works relatively well. And yeah, I'll end with some conclusions. So, sea ice and modeling sea ice. First of all, why do we model sea ice? As all of you probably know, it's a fundamental component of Earth's climate system. So when people talk about the influence of sea ice on the climate system, you'll often hear people talk about albedo and sea ice's role in the energy balance of the planet, but also its role in ocean circulation and how it can really affect the stability of currents, right? Ocean currents. Just to kind of mention that sea ice, as you see in this photograph, people usually talk about 2 parts of sea ice, right? There's a central ice pack, which you would see in this satellite image, which is of the Fram Strait between Greenland and the Svalbard Islands. You have the central ice pack to the north, where you really can hardly see a distinction between ice floes. When I talk about ice floe, by the way, I mean FLOE, which kind of refers to a chunk of ice, which can be kilometers large. But in the central ice pack, it's difficult to distinguish between different ice floes, and these sort of deform into each other through processes like ridging or rafting or welding. And then you have the marginal ice zone, where you can really see these distinct ice floes, and that's more around the edge of the central ice pack. So these are 2 very different regions. I won't really make distinctions between them because I think I'm just talking more of a methodology that should apply to both, but it's just good to know that. It will come up. And when we model sea ice, which is something we're interested in doing because of its importance for climate, people usually use 2 approaches. So a very common approach is to model sea ice like a continuum that's floating over the ocean. And essentially, people usually treat it like a viscous fluid. and this will be a big part of the talk, how this viscous fluid is described. And the advantages of using a continuum model is that it's much cheaper to solve numerically. The disadvantage is that oftentimes it's not very accurate. And there's a lot of conversation around how we can make these continuum models more accurate. But since they are cheap to solve, they're usually used in Earth system models when solving the whole of the climate system in this integrated way. Now, a second approach, which people consider to be much more promising, are discrete element methods. So here I wrote model, but this should actually be methods, but I'll just be using the acronym DEM. And essentially here what we do is we model each ice flow separately by Newton's law, and then we parameterize interactions between ice flows with different models, really. This is very expensive, yet, as I said before, it's considered a much more promising avenue to achieve accurate predictions. And essentially the goal of this talk will be about inferring a continuum model from DEM data. And I'll make that more clear now throughout this introduction, what we want to do exactly. But before that, I just wanted to go a little bit more in depth with what these different models do. So discrete element methods, as I said, they're based on a Lagrangian description of ice flows, which means that we basically solve Newton's laws. So this is force balance. We also solve angular momentum balance. And essentially, we have that the acceleration of the ice flow is due to ocean drag, wind drag, and then collisions and other interactions between ice flows, as you see here in this little diagram. Now, I'm going to be using a very, very special discrete element method that was developed initially by Georgi and Brandon, who are also part of the Sea Ice project, Sea Ice Muri project, sorry. Even though I've been using a newer version that was developed by Skylar Gehring at Caltech. It's implemented in Julia, and it's honestly fantastic. It's incredibly efficient, and it's been great to use. Now, what makes SubZero very, very special is that on the one hand, we have polygon-shaped ice flows, which is something that not all DEMs have, even though the newer generation of DEMs start having polygon-shaped ice flows. And they have a whole lot of parameterizations for all these flow interaction processes. And just to show you how impressive these computations look like, here I have a video from their website. It's going to be a simulation of these different interlocked ice flows essentially being deformed by 4 ocean eddies. And the heart you see in the middle is a solid island that will not deform. So I'll just play the video so you see it. So you start seeing how everything starts deforming. It might seem like we lose mass, but SubZero has a module that makes ice flows disappear when they become very small, but somehow they conserve their presence by including a force in the ocean. It's a bit strange, but it's required for computational reasons because ice flows just start breaking too much and just becomes impossible to track them. A little spoiler, I won't consider fracturing or any kind of mechanical deformations in the computations I do, just because I think these are very complicated processes that rely on ad hoc parameterizations. We want to kind of stick to more solid mechanics, like what you get from collisions, for example. But anyway, that was just to give you an impression of what SubZero looks like. You'll see more videos in the following slides. Okay, so that's discrete element methods. But as we saw, the other class of methods are continuum models. So one big difference is that instead of a Lagrangian description, we have a Eulerian description. So a spatially based description of conservation of mass, momentum, energy. In this case, I show you conservation of momentum because I think it's interesting to compare this with the previous equation I showed you for conservation of momentum for a single ice flow. Again, we have inertial forces balanced by ocean drag, wind drag, and then internal forces that now take a very different flavor. Now we have the divergence of a stress tensor, right? And ocean drag and wind drag, they're parameterized with these quadratic formulas. Usually wind drag, tau A, is made independent of the ice velocity. So the ice velocity would be U, just because UA is typically much larger than U, so the difference is negligible. And basically, what we need to close this system of equations whenever we consider sea ice to behave like a viscous fluid continuum, which is a very common assumption, is what is called a rheology. What is a rheology? A rheology is a relationship between the Cauchy stress tensor sigma and the strain rate tensor. Of course, there are other parameters that influence a rheology. In particular, for CIs, we'll care a lot about concentration, A. So from now on, A is going to refer to the concentration of CIs at a point. There'll be a number between 0 and 1 in this continuum. Another typically very important one is the ice thickness H, which for simplicity from now on, I'll forget about. We could include it in our inference system, but for simplicity, we don't. But typically, you have to consider it. And essentially, this rheology captures a spatial and temporal averaging of all the kind of flow interactions that are happening at the microscale. So collisions, fractures, ridging, etc. So this is why a rheology is on the one hand very, very difficult to describe because a lot is going on, but also so important. This will really determine the sea ice dynamics of the ice pack, right? I just want to give a sense of how people have modeled sea ice in the past by just going over a few models for sea ice. So the most famous one is Hibbler's model. I'm sure many of you here have heard about it. Hibbler's model was first proposed in 1979 by Hibbler himself, obviously. But he basically used ideas from a few years back developed by members of the AJAX project, which was this Arctic Ice Dynamics joint experimental project, a joint US and Canadian project that really provided a lot of advance in the field. And basically, in the AJAX project, some of their members thought a lot about how we could model sea ice as a continuum. And what they thought was that essentially in the central ice pack, we have internal stresses, mostly due to the formation of pressure ridges, which is what you see here. So these are two flows that collide, and then they deform into each other through compression. And basically, by a very simple energy argument, they argued that we should have a plastic rheology. Hibbler came a few years later, and to simplify the math, and based also on a nice statistical argument, said that this should actually be a viscous plastic rheology. Whenever you have a plastic rheology, a plastic model, you basically describe it in terms of a yield curve, which gives a very cool geometrical interpretation of how the material reacts to stresses. And Hibbler proposed an elliptical yield curve, which simplified the math a lot. And there's a lot going on here. Basically, a yield curve is usually drawn in the plane of principal stresses. But what it's telling us is basically that ice locally has no resistance to expansion. So sigma 1 is the principal stress that refers to pure expansion, pure compression. And that means that if two ice flows drift apart, that doesn't require any energy. However, compression, you do require energy to compress, essentially because you're producing a pressure ridge. So anyway, that's the rationale behind it. That's Hibbler's model. I get the impression that most of the models in Earth system models for sea ice, most of the modules rely on either Hibbler's model or variations of it. So this is fundamental to sea ice. And that's a great example. More similar to what we're going to work with our collisional models, which really use kinetic theory to derive a rheology. And there's been a great result recently from Srikanth, who has derived a continuum model for sea ice based on a mean field representation of collisions. Great work, and he derives a linear viscous rheology. Another set of models, which I find very interesting, and Georg and I and some other collaborators also worked on this, is using ideas from granular media. In particular, there's a type of regime of granular media called granular floes, dense granular floes, that essentially try to describe mechanics that could be quite similar to sea ice. So to try to describe this, what I write here is that dense granular flow models describe an intermediate regime between what are called quasi-static dense granular concentrations and dilute concentrations. And there's a very nice analogy with the three states of matter. So essentially, one can think of quasi-static dense concentrations as a lot of grains packed together, behaving almost like a solid. And on the other hand, another extreme, you have grains moving with a lot of energy and colliding with each other, like as if they were molecules in a gas. And just to describe this better, I show this illustration here from a couple of papers. where you have a very typical experiment in granular media, which is the formation of a column of beads by just dropping them from above. And essentially, if you look at a video of this, you can distinguish between three states roughly, right? So you, on the one hand, have the beads stacked up towards the center of the pile, and that behaves like a solid that under sufficient shear will start deforming. So that's what they mean by a quasi-static dense concentration. On the very top, you have beads just flying all over the place and every now and then colliding. And when they collide in binary, uncorrelated, instantaneous ways. So that would be the gas regime. But in the middle, you have something that's kind of in between, right? So you basically have the beads that on the one hand, they're colliding, they're moving quite a lot, but they're constantly in touch. And it's this kind of constant rubbing and friction that determines the overall dynamics. And there are these models for this regime called the mu of I models, which a few years back, Agnieszka Herman suggested they might be very good models for CIs. And what's very nice about these models is that on the one hand, they provide a pre-existing functional form based on some phenomenological arguments, which only require you to determine a single scalar function, which is a mu of I function, which essentially is what they call an effective frictional coefficient. So there's quite a lot of analogies with Coulomb's friction law here, which has also been applied in special ways to quasi-static dense concentrations. But then this frictional coefficient depends on a factor called the inertial number I, which essentially is a measure of how important collisions are. So the larger I is, the more collisions you see, and the lower I is, the less collisions you see. And we basically spent some time working on this model. We published this paper with other collaborators from the CI-SMURI project, where we essentially used SubZero data. So SubZero is a discrete element method I showed you before, to infer a model that would more or less replicate the velocity fields we see in SubZero by fitting this mu of I function. We had to do a little bit more work. It's a bit messier than that, but it's quite cool to see that we arrive at a viscoplastic model, which in many ways is sort of similar to Hibbeler's model. In other ways, it's not. That doesn't matter too much, but this is just an example of another approach to modeling CIs, using a pre-existing functional form based on some phenomenological arguments. Okay, so what I just said is sort of, again, going back to this idea of different ways of modeling CIs, and we saw that some are purely analytical, based on simple energy arguments, or mean field representations of collisions, and others are data-based, like this mu of I model, where we actually have to fit a function somehow, but we have a pre-existing functional form, which really narrows down the amount of fitting we have to do. So we want to continue this, what we did in our previous paper, what I showed you before, where we used data from SubZero to find the rheology, but we no longer want to have a pre-existing functional form, which in this case of the previous paper, this one was this mu of I framework. And that's our goal for today. That's the goal of the work I've been doing until now I'm presenting today, which is to present a data-based approach towards finding a rheology for CIs that does not make any ad hoc assumptions about the functional form of the rheology. And I'll use SubZero data to do this. I'll find a rheology that reproduces the velocity fields we see with SubZero. And why is this important? Well, I think this is important because we're basically introducing an approach that would allow us to, on the one hand, retain the accuracy of a discrete element method if we're able to do this inference the right way, but we would arrive at a continuum model that is much less expensive to solve in the discrete element method, right? So essentially, we have the potential of retaining a DEM's accuracy at the computational expense of a continuum model. So that's the introduction, and I'll dive into this mathematical framework for doing this. So the first question is, okay, we're going to build a general rheology from data. We could think of a very general rheological model, but to start with, we're going to narrow down our possibilities to explicit and local rheologies. And as I said before, we're going to consider the dependence on the concentration of sea ice A. We're going to forget about other factors. We could, for example, consider ice thickness, number of ice floes. But here we're going to concentrate on the dependence on the one hand, the strain rate tensor, du, and on the other hand, the sea ice concentration, A. And a general model for such a rheology would look like what you have here, where our Cauchy stress tensor sigma is given by, on the one hand, the pressure, and then on the other hand, an additional term, which is essentially depends on how you understand the pressure, but we can just see it as something that maps from strain rate tensors to stress tensors. So essentially we have a map C from symmetric matrices to symmetric matrices. And this is the fact that it's a local model. We're only considering the dependence on one spatial point. If it was a non-local model, C would have to be a map between tensor fields, but we're not considering that for now. Okay? Okay. This is still very general, and it's quite delicate. Say, for example, I just define a neural network that maps symmetric matrices to symmetric matrices. We risk violating a lot of physical principles if we do that without any care. So in order to be physically sensible, we restrict the functional form of C by considering isotropic models only. So what do I mean by an isotropic model? Essentially, we can define an isotropic rheology in terms of the map C by enforcing the property that we have this invariance to rotations. So what you see here is a property where for any symmetric matrix M and any orthogonal matrix Q that represents, for example, a rotation, we have this rotational invariance. What does this mean? Well, it essentially means that we have a fluid whose viscosity will be the same, exhibits the same mechanical properties independently of the direction of forcing. And this is fantastic because if we restrict our attention to isotropic rheologies, we can use this very powerful result, which dates back to the 50s, to work by people like Ericsson and Rivlin, that characterized all possible isotropic maps. That is, if you have a map between symmetric matrices C that satisfies the isotropy property I showed you before, then it will necessarily, these are if and only if conditions, be written down in this form. That is, it will be characterized in terms of two scalar functions, psi1 and psi2, that only depend on the principal invariance of M. Since here M is a 2x2 matrix, we only have two principal invariants, which are essentially the trace and, say, the Frobenius norm. That's two ways of characterizing these principal invariants. And this is fantastic because essentially this is already giving us a framework, right? Perhaps what we could do is simply fit the functions psi1 and psi2 with some kind of interpolator to SubZero data. If we do this, the advantages are the following. On the one hand, we automatically satisfy the principle of frame indifference. That's a kind of Galilean invariance, right? So we can ensure that at least key physical principles, symmetries, are satisfied. On top of that, something very nice about this is that if I generate data in specific experimental conditions, if an underlying rheology does exist, we can expect to learn properties that are intrinsic to the material and independent of those experiments. And in particular, this will allow us to integrate very different data sets when fitting these functions, since we're only working with invariants that shouldn't depend on conditions of observation of experimental data. So this is essentially the essence of our framework, right? We use this theorem that characterizes isotropic maps to reduce our rheology to this functional form, and then we fit these two functions that only depend on principal invariants. Okay, we're going to make things a bit more simple, because if we're going to consider a general compressible fluid, and there's very good reasons to think of sea ice as a compressible fluid, we need to discover these two functions, psi1 and psi2, plus an equation of state for the pressure P. So there's a lot going on here. And we're thinking about how to do this. We have some ideas. But today I'm going to present something slightly more simple. I'm going to reduce things to one dimensions. I'll talk about how this can extend to 2 dimensions later. But I'm essentially going to reduce this discovery process of our rheology to a one-dimensional setting by working with SubZero data generated by forcing the ice with strictly horizontal ocean and wind forcing that is independent of x. That is, the ocean currents and the wind currents that will drive the ice flows will be from essentially east to west, if we think of our domain as a square patch of ocean with the cardinal directions. And essentially, we'll assume that these velocity fields are independent of x. And the thing is, mathematically, if the forcing satisfies these conditions, then it's natural to expect the sea ice velocity u to also be purely horizontal and be independent of x. And if that's the case, then the equations of motion for sea ice, that is the equations of conservation of momentum, reduced to what you see here, down here. So this is essentially force balance in the horizontal direction, inertial forces balanced with internal stresses and ocean drag and wind drag. But more interestingly, the rheology, which now depends on a pressure on psi1 and on psi2, reduces to a single function, psi, which now only depends on one of the principal invariants, because essentially the trace becomes 0 under these conditions. So instead of having 2 invariants, we only have 1. And that's what you see here. Psi is essentially psi2 with the trace set to 0. Okay, so here, psi is going to be the only rheological property we'll be able to see in this one-dimensional setup. And that's what we'll try to learn in these tests. So we will learn the dependence of psi2 on the second invariant and on the concentration. You can think of psi as an effective shear viscosity. And we will be able to extend results to 2D whenever we assume the fluid that represents the sea ice to be incompressible. So I'll show results about this later. But this is essentially the framework I'm going to be following, okay? One-dimensional setup where we can discover this rheological property that represents the effective shear viscosity. Okay? Are there any questions here? If not, I'll proceed to talk about the kind of data I'll be generating. So you can think of this as a training setup. This is the data I'm going to use to train the model. Later on, I'll show you very, very different tests. We'll show you that our rheology works quite well. But the training is essentially going to be in the following setup. We're going to consider a periodic patch of ocean where the sea ice is driven by a shearing ocean current like this. So it has this hat function. Remember that it's independent of x, the profile of u. You see that here, u, o, y. On top of that, the ocean velocity is going to be steady, and we're going to drive the SubZero computations until a steady state is reached. And as I said before, I'm not going to consider deformation of ice flows. Something interesting that especially Georg spent a lot of time on was we came up with a way of representing what they call a power law flow size distribution. So we have something that looks kind of realistic in terms of the distribution of flow sizes. I'll talk about that now, but before that, I want to show you a video of what these computations look like. So this is one of the training setups. So you see that we drive the ice with this hat-shaped velocity field. We drive it for around 2 days. You can see that the velocity, the ice flows move faster in the middle than on the sides, but the velocity of the ice flows is not completely 0 here. So there's some transfer of momentum in the north-south direction. That's essentially what the rheology is, that there's this transfer of momentum through collisions and friction. So yeah, so these are the computations that we do to generate data that will allow us to train our rheology. I'll say a little bit about how we did it to achieve a power law distribution. This was really Georg's work. He spent some time thinking about this. So essentially, flows, if you work with observational data from satellites and you're able to infer the areas of different flows, it turns out that it's quite common to see a power law distribution where essentially you have many, many more flows that are small than those that are large. And that distribution, that kind of histogram, when plotted in a log-log plot, log-log scale, it takes a power law. And we achieved this in SubZero by essentially developing a Voronoi tessellation of the domain based on a point cloud that is based on a series of generalized gamma functions. So there's a lot going on here, but it turns out that if you use a uniform distribution of random points on your 2D domain, so you seed it with points that are uniformly distributed, and then based on that point cloud, you develop a Voronoi tessellation, your flow size distribution will be a generalized gamma function. And if you scale it differently, you get different flow sizes. So if you combine different generalized gamma functions with different weights, you can achieve a power law. But you still have to figure out what those weights alpha are in this kind of combined scale gamma function distribution. And to do that, we did an optimization where we basically minimized the misfit between our combined gamma function and the power law distribution in this kind of like log mean squared residual way. Anyway, with this approach, we were able to find a power law distribution, which is what you see here, which I guess it's hard to tell that this is a power law distribution, but it is. So that was quite cool because that's what you find in nature, apparently. Okay, so we do many of these computations for different ocean velocities and for different concentrations. And for each of these computations, by averaging over these grid cells, which here are horizontal because we don't expect properties to change in the east-west direction, we can extract the following information. We can do an averaging of ice flow velocities. Based on this averaging of ice flow velocities, we can find, by simply differentiating with finite differences, we can find strain rates. But on top of that, we can also extract shear stresses by using the so-called Love-Weber formula, which gives an idea of how stresses arise from collisions between particles. And basically, this allows us to find two data sets, what I call a kinematic data set, which is just based on horizontal velocities, and a dynamic data set, which is based on strain stress pairs. So we have these two different data sets. And just to give you an idea of what these velocity profiles look like, essentially, we will find some states where the ice velocity, which when averaged at its steady state, is given by these black dots. Everything here is normalized with the maximum ocean velocity, which is U_0. Sometimes we get basically free drift, where the ice pretty much follows the ocean current. That means that there are very few collisions, and we usually get this for very low concentrations. And as we increase the concentration, the momentum transfer between the ice flows in the north-south direction becomes stronger and stronger to the point that we get this, which I call a solid-like translation. So it's precisely this intermediate where the rheology is essentially manifesting itself, right? So capturing this transition is going to be the essence of our rheological model, right? This is what encodes this momentum transfer between flows via collisions. Okay, so as I said before, since we're in one dimension, we only need to fit one function psi. And what we're going to do is represent psi as a neural network, which I'll talk a little bit more about that before. And we're going to fit it to SubZero data in two steps. First, we're going to minimize the stress misfit, which, as I'll show you later, is a standard nonlinear regression. But then we're going to do something more interesting, which is we're going to minimize a velocity misfit. And this will essentially be a PDE-constrained optimization problem, which I'll show you how we solve in a couple of slides. And why is this important? Well, basically because we're interested in reproducing SubZero's velocity field. That's essentially what we want to do. But more importantly, the stress data from the DEM, which is computed from this Love-Weber formula that I talked about, that is derived in granular media theory, gives very noisy data. It's really unclear if there's an underlying rheology. So we trust the velocity data more. And more importantly, if we're able to develop a method that only relies on velocity data, it opens the possibility of actually using this with observational data where velocity fields are readily available as opposed to stress data, right? How do you infer stress from satellite imagery? It's strange, but you can definitely infer a velocity field. So that's our rationale for doing this minimization of the velocity misfit to infer a rheology. Now for the computational setup, as you said, we represent the rheology with a neural network. In particular, I do a combination of two neural networks with an exponential that looks like this. So we essentially have a scaling term that only depends on the concentration A, and this accounts for large changes with concentration. And on top of that, I have a non-negative neural network here. By making it non-negative, I enforce the second principle of thermodynamics, right? I have only a strictly positive shear viscosity. I use a very, very small neural networks. So each neural network has about 50 parameters. So it's really a very simple interpolator, but it worked well with PyTorch. And more importantly, it worked well with the general computational framework that we've been using. So this is what I talk about here. So the fact is that as soon as we represent the viscosity with a neural network, we have what I like to call a neural network-based partial differential equation. And the fact is that we have to solve this partial differential equation because when we do the velocity minimization, we have to do a PDE-constrained optimization problem where we have to solve this PDE many times. I solve it with the finite element method, and I use a module called Firedrake that maybe some of you have heard about. But I use Firedrake because just in the last year, there's been awesome developments by some of our members of Firedrake where they explore the integration of PyTorch into Firedrake in such a way that the automatic differentiation of both Firedrake and PyTorch are embedded. So basically, this allows me to take derivatives of functionals involving this PDE without having to compute any derivatives by hand. So this is extremely powerful. It's hard to emphasize just how powerful it is. Something I wanted to talk about very briefly, because I realize I'm taking up more time than I thought. I thought I had a lot of time, is that we have to solve this PDE many times. And when I first did this, I realized that the PDE would crash very often because I would be working with a rheology that had that as a consequence of which the PDE was not well posed. So that made me think, how can I enforce properties on the neural network such that the PDE is well posed? It has a unique solution. And one way to do this is to enforce a robustness, the monotonicity of this map, the map from the shear strain to the product of the shear strain times the viscosity. Because if we do this, then we have that the PDE that you see here is equivalent to the minimization of a convex functional that will have a unique minimizer if it's not just convex, but it's strictly convex. So as you'll see later, we penalize some elements of the misfit functional to enforce this monotonicity property. And that improves the robustness of our method significantly. Okay, so I'm just going to talk about results now. So you'll see that I'll do first stress strain fit of the data. And this is what the data looks like of the different SubZero computations. So here, you have clusters of points that correspond with different steady states. This is a velocity data, and this is a stress strain data. And once I fit the stress strain data, I fit the velocity data. Those are the two steps of the optimization. In step one, we minimize the stress misfit. It's a kind of like log misfit to account for big changes in the stress with the strain. As you see, this is in log scale. I penalize this monotonicity of the functional that I showed before to ensure that I get monotonically increasing stress strain curves, because that will allow me to solve the PDE much more easily. And this is what the viscosity looks like. And it's very cool to see that for the 4 different concentrations for which I fit the data, which is like 80% concentration all the way to 95%, we go from a shear thickening viscosity to a shear thinning viscosity. Okay, so this is minimizing the stress misfit. The question is, what do the velocity fields look like? The velocity fields that I get once I solve the PDE defined in terms of the neural network psi. And this is what it looks like. In general, I get a very, very good fit to the data. So this is a velocity data for the different steady states. This is a normalized velocity field. So that's why it looks like the same. But in reality, this is a very slow ocean current of 0.05 meters a second. This is a very fast ocean current. This is for low concentrations. And down here, you have high concentrations. That's why it looks much flatter. And what you see is that in general, we actually get a very good fit. But we still have some cases around here where the fit is not perfect. So we improve that by now minimizing the velocity misfit. So we use the weights that we obtained in step 1 as our initial guess for the optimization. And now we do this PDE-constrained approach, where you see that we're minimizing the L2 difference of the velocity fields. Here, this is a data UI for each steady state from SubZero. And this is the solution of the PDE that now depends on the concentration, but also on the weights of the neural network. And if we do this, we see that we get slight differences in the results. So the dotted lines were the results from the previous step, and the straight lines are the new results. So we get some changes in some of the lower concentrations. In general, it seems that the velocity prefers a less viscous solution. But it's very cool to see that now, if you look at the velocity fields, we get pretty much a perfect fit. So the red lines are the new velocity fields that improve those small errors we saw up here before. And in fact, if we look at the average L2 velocity error, we see that we reduce it in 1 order of magnitude. So basically, this is a proof of concept. Our training approach does work. We're able to fit those velocity fields using velocity data. And here I just wanted to say that I don't have much time, so I won't talk much about this, but we get a shear thinning behavior and a shear thickening behavior that contrast strongly with existing models. I didn't do comparisons, but we get much, much better results with this approach than with existing models. And what's interesting is that this shear thinning behavior for high concentrations and shear thickening behavior is actually present in the DM data. So what you see here is that for low concentration, so this is 80% concentration, you see that for very low velocities, we get free drift. The ice follows the ocean velocity very closely. But as we increase the velocity and we increase the shear, we start moving towards a flatter profile. And you can show with a very simple dimensional analysis that this can only hold if you have a shear thickening rheology. So basically, the DEM data is telling us that, yes, this has to be shear thickening. On the other hand, for very high concentrations, we see the opposite. For very low velocities, we get a purely flat velocity profile, which means that it's very viscous, it's very resistant. But as we increase the velocity, somehow we transition towards a flatter profile, a more curved profile, which in some way could be the result of shear thinning. It doesn't necessarily have to. It could be shear thickening at a very low rate as well. You can show this again with a very simple dimensional analysis. But what I want to show with this is that our results are sort of consistent with what the DEM data is telling us. And I think this is a very interesting result, which I'm still thinking about. I don't really understand the underlying mechanisms that drive this transition from shear thickening to shear thinning, but it's quite interesting insight that I hadn't seen anywhere else. Okay, so I'll go very quickly over this. But basically, the training you've seen is very simplified, right? It's on the one hand, one-dimensional, steady conditions. There's no wind forcing, and all the ocean velocities were essentially the same. They were just scaled with increasingly strong ocean currents, right? But very simple. So I essentially want to test our model by comparing results with SubZero in very different conditions. So I'll do a first test problem where we have unsteady conditions in 1 dimensions, where we have both ocean and wind forcing, and these are randomly generated profiles. So they're not simple velocity profiles anymore. And second of all, I'll test a 2-dimensional problem that we can test if we assume the fluid to be incompressible. That allows us to extend trivially to 2 dimensions. I'll tell you how. But what I want to say is that for these test problems, as you expect, we do not change the network weights. Those are the ones achieved through the optimization you saw in the training step. And we tune no additional parameters. So this is really like pure unseen data. So for the first test problem, we have unsteady conditions. So now we have to include this term in the equations of motion. It's still 1-dimensional, but we essentially have a static ocean velocity that looks like this. This is randomly generated with 2 Fourier modes. But then we have oscillating wind velocity. So it's oscillating in this harmonic way in time. And the wind velocity profile looks like this. Sorry, here I wrote UW, here I wrote UA. Sometimes I write UA for atmospheric air. Sometimes I write UW for wind. But this is what the kind of static profile looks like. And then we're oscillating that from left to right. If you look at the data, this is what SubZero looks like. So you see that it's mainly wind driven. The wind is much stronger than the ocean. So it's really driving, the wind is what's driving the flow. So they move from left to right in this way. We're also testing it on a concentration of 87.5% of sea ice, which is also unseen. If you remember, we trained it on concentrations of 80, 85, 90, and 95%. And basically, if we take the SubZero data and compare it with our PDE results, this is what we get at 4 different instants in time. And I'm quite happy with the results. So they're not perfect, but given that all of it is really based on purely unseen data at many levels, concentration and the conditions, I think it's quite good. In particular, it gets better with time, which I think is because somehow it starts arriving at a steady state, I think, over time. Anyways, I'm not too sure. I haven't thought about it too much, but overall, we get a good fit, showing that our model can generalize beyond the training setup. If we look at 2 dimensions, we tested on a very simple model where essentially we consider the kind of hat profiles that we had before, but now they curve along these streamlines that you see here. And essentially, we can solve our PDE in 2 dimensions if we assume the fluid to be incompressible. Because if it's incompressible, on the one hand, one of the functions, psi1, gets absorbed into the pressure, which is given as a Lagrangian multiplier of the divergence-free condition. And one of the invariants, the trace, is trivially 0 because it's divergence-free. This is what the SubZero data looks like. You see that the ice curves upwards, so it's like 2-dimensional problem. And if we compare it with our PDE that we saw for the incompressible model, we get decent results, I think. It's still strange. Here, the red lines, this is the velocity fields along 3 different sections, cross sections. And we see that the results are quite similar. In the middle, it's a bit strange that we don't get purely horizontal data for the DEM. I think that's because we still didn't really arrive at a steady state, but it just took so many time steps that it took like a whole day to compute. So I think I have to run it for even longer, because after running it a bit longer, the vertical components of the middle section, which by symmetry should be 0, become smaller. But in any case, I think it's quite decent results, given that it's a big step to assume the model to be incompressible. Ice is certainly not going to be incompressible. Okay, so that's it. Okay, it's still 10-2. These are the conclusions. Essentially, what you've seen is the inference of a neural network-based rheology for 1D sea ice models and incompressible 2D sea ice models, which we achieved by coupling Firedrake and PyTorch. And we enforce key physical and mathematical properties in the model's architecture to ensure, on the one hand, that the model is physically consistent, and on the other hand, that it's mathematically robust to allow for this PDE-constrained optimization. Just some remarks. It's accurate for 1D problems and for these simple 2D problems. I think it provides interesting insights into the collisional dynamics of polygonal ice flows. This kind of transition from shear thickening to shear thinning, I think, is very interesting, something I want to think about much more. But not everything is perfect. For certain 2D problems that start becoming more complicated, we do not get good results. And it's obvious because we should include compressible models that allow for redistribution of the ice concentration locally. We cannot achieve that with incompressible models, and we see that with SubZero data. Also, I use neural networks, and honestly, I'm not convinced that they're the best way to proceed, because the optimization becomes horrible. I spent so much time optimizing, just tweaking parameters in the optimization process to achieve a decent result. So I definitely want to think of alternatives to neural networks. But anyways, I think for future work, what we're looking at right now is incorporating more complex physics. In particular, compressibility is very important. I think non-local effects could also be included by using convolutional models. And then I really want to think about how some of this approach could be used with observational data, which is much more scarce, just asking the question of how much we could possibly infer. Anyways, that's it. I'm sorry for rushing. I think I really didn't measure the time too well, even though I'm still on time. I think I had to rush more than I expected. Some of the results you see today will be published very soon. Jürgen and I are currently writing up 2 different papers, one very technical, another more for like a physics crowd. So watch out for that. I hope they'll be out in a couple months. And thank you for your attention. And please feel free to ask any questions.
Okay, great. Yes. Yeah. Please thank Gonzalo. That was a great talk. Clapping hand emojis, of course, if I can find them. There we go.
Oh, great. I can't see anything. I'm still just seeing.
That was a very great talk. Really, really interesting. Yeah, so I think we do certainly have time for some questions. Does anybody have a question they wanted to ask?
I have a very simple question. So
Yeah.
You mentioned that earlier that you would like to use observational data. So the data that you're using is synthetic. So how are you generating this data that you're using to fit your model? Correct.
I'm generating it by solving DEM problems. So essentially, we have this solver, SubZero. Excuse me?
No, I did not say nothing. Sorry. I mean,
oh, sorry. So basically, what I do is I do computations with this discrete element method that solves for each ice flow individually, like you see here. And then I have a method for averaging over a grid, which gives me gridded Eulerian data. And that data can be used to fit the model, because I get, on the one hand, a velocity field that evolves in time, but I also get a stress strain field. So those are the data points I use to do the inference of the neural network weights theta. Okay. At the end of the day, I rely on velocity data. So I think if I were to use observational data, somehow we'd have to think of restricting the problem setting to something that's solvable with PDEs by maybe looking at a patch of ocean and thinking of the correct boundary conditions, and then using velocity fields that we get from observations to do this PDE-constrained optimization based only on velocity data. We would also need, actually, like, this is a caveat, but we would also need, this is a limitation of observational data. We would also need some information on wind and ocean forcing, which we'd have to think about how to infer or obtain. Does that make sense?
Yes, yes. So basically, if you're using observational data, I mean, you have to take into account more physics into your model. Is that correct?
I think if we have a proper two-dimensional approach that's for compressible fluids, I think in principle that should be enough. I think the problem will be that the data will just be very scarce. And the question will be, how much can we infer from that? So maybe we would have to start from DEM data and then add an additional optimization process where we see what additional information the observational data tells us. But I think the physics that is integrated in our model should be enough. I don't know.
Okay. Can I actually follow up on it? Just as you were talking about it, it made me think, because, yeah, I sort of was wondering, I mean, one thing you could do to see how much data you would need would be to look at, change the resolution of the data you get from the DEM and see how well the results are, right? Use less. But then, interestingly, if you have one of these DEM models and then you have some synthetic aperture radar data, maybe some wind data, other data over this patch of ocean, could you use something like data assimilation to create basically a reanalysis of what the ice was doing with the DEM, assimilating all the relevant data so that you then had a DEM run that was based on whatever observations you can take, and try to use that as a training set?
That's such a good idea, and absolutely, yeah. In fact, there's a bunch of folks in the CI's Muri working precisely on data assimilation using SubZero.
Oh, interesting. Okay, very cool.
Yeah, Nan Chen and his group, that's what they're doing. So yeah, that's a great idea. So that would mean that we still use DEM data. We somehow tune the DEM data to observational data, so it's containing some of that observational data. But we're still in this synthetic setup that allows us to do what we want with data generation.
Right. Yeah, that's exactly what I was thinking. Yeah.
Yeah. No, that's definitely a very, 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 very good idea. Yeah.
Cool. I had maybe just one more. So you use this power law with the flow size distribution, which changes with your distance from the ice edge. The power law can change behavior. And so I wonder if you, I know this is a proof of concept to start, but I wonder if you thought about what it might be like if you were to sort of zoom out with a much larger domain where you have different flow size distributions, and how that might either make things more complex or change things.
That's a great question. One of the reasons we wanted to enable power law distributions is because eventually, if anyone's interested in this, I think it could be very cool to test this inference with different flow size distributions to see the effect of these power law exponents, for example, on rheological properties. So I think at the end of the day, we can really generate the flow size distribution we want, and with that we can extract a rheology quite easily. Like, the optimization process is the same one, so that shouldn't be a problem. If I understood correctly, because you were saying that perhaps one has to take into account more complex flow size distributions, right? In a wider scale. Like
yeah. So, at closer to the ice edge, you'll typically have a much higher number of smaller flows than you do further away. And then having a domain that covers, where the flow size distributions transition, so that you'd have really, I guess, these just transition points in what the ice looked like in terms of the flow sizes, and how that a domain that large might affect things. I don't know.
So what we show here, I think, could integrate those additional parameters, which refer to, I guess, the morphology of flows and locally, by perhaps considering the dependence of the rheology on not just the concentration, right, but perhaps the flow size, or some scalar field that tells you something about the local flow size in an area. You see what I mean?
Mm-hmm. Mm-hmm. Yeah.
I think that could definitely be introduced, and you would expect to see some variation of rheological properties with flow size, and perhaps that's a way to take that into account, which we don't here. We just ignore the dependence on flow size.
Right. Okay. Yeah, that's really interesting.
Yeah, I guess the power law distribution is just to try to make it look more realistic, and I guess to sell the idea better. But at the end of the day, a rigorous integration of the importance of the flow size into rheology would require exploring the parameter space of flow sizes as well.
Right. Really interesting. Yeah, this is cool stuff. I could keep going, but does anybody else have any questions?
No questions. Just thanks for a great talk.
Thank you.
Okay, maybe just, sorry, one last quick one. So I understand using these DM models is desirable. Have you thought about using any other models to see how well at least the method can reproduce the rheology? So there's one that I'm thinking of that Deborah Selsky at the University of New Mexico developed, where she has this elastic decohesive rheology where she really tracks cracks in the sea ice. So it's a much different regime than a bunch of flows and things. But you could, in principle, I suppose, try to see if the method is robust in recovering some of these kinds of rheological properties.
Yeah, that would be very cool. I agree. I guess, and that would just be the question of, can you find that local explicit rheology that reproduces the results of this much more complicated elastic rheology, right?
Right. Yeah.
That would be.
That seems worth it, or if it's.
What we have here really is an interpolation method in a way.
Mm-hmm.
So if you give me the data, I can interpolate it, and then the question is, how well does that data adapt to a function, right? So.
Right.
So I guess. So we can definitely try. Yeah. I'm not sure how well it will work, because you're trying to approximate an elastic model with a viscous rheological model, right?
Right, which is kind of, yeah, okay, good point.
But we can definitely try. I think that the data, the spatial distribution of data will tell us if this works or if it doesn't work. But if you give me data, I can definitely fit it.
Sure, yeah, okay. Yeah, I can certainly send you some papers, and yeah, if you're interested in looking at it. Yeah, okay.
Great.
Cool. Okay, any other questions or? Okay, then let's thank Gonzalo again. It was a very great talk, well presented, and much appreciate you being willing to present to us. So I guess.
Nice talk. Thank you.
Thank you very much.
Okay. All right. With that, then I guess we'll see. I think this is kind of our last talk of the summer. So thank you for closing us out, Gonzalo. It was a great closing talk. And I think we'll pick up in the fall.
Great.
In September. So yeah, great.
Great. Thank you, Christian.
Thanks, everyone.
Bye.